The manufacturing process of double valves at Double Lin begins with in-house forging, impressing, and tempering of all metal components to ensure strength, stability, and resistance to wear. After thermal treatment, product surfaces are processed through a finishing step called finalizing, which improves smoothness and durability. The machining process is carried out using advanced automatic special machines based on manipulators and servo motors. These machines perform dual cutting operations using profile cutters, guaranteeing precise dimensional uniformity. This transforms rough and semi-finished parts into components with 4 times higher efficiency than traditional methods. Ball automatic special machines further streamline production by shaping critical dimensions in a single step, replacing the original 3-step process. This reduces clamping times and handling errors, minimizing product damage and improving surface quality. Diamond cutter bits achieve a high surface finish of raw 0.8, ensuring no leakage even after 10,000 cycles. Valve rod automatic special machines solve the problems of traditional machines with low efficiency and accuracy. The upgraded equipment enhances precision throughout the transformation of copper bars into valve rods. For sealing elements, PTFE seal rings are produced using fully automated extrusion molding machines. Double Lin sources high-quality raw materials and avoids outsourcing to maintain strict quality control. Chamfered designs create smooth, durable, and user-friendly components. The final assembly is completed on fully automatic lines imported from Italy. Equipped with infrared inspection systems, these lines require only one operator and can perform precise assembly tasks that would typically need 13 workers. This automation not only increases productivity, but also ensures consistent quality, completing Double Lin's efficient and technologically advanced production system. Molten gold was poured into molds at Detour Lake Mine, forming 4 bars weighing about 2,000 ounces. After solidifying, the glowing bars were carefully lifted and cooled. Marked with identifiers, the bars represented the first gold production milestone, achieved through teamwork, precision, and months of preparation. The motor rewinding and reassembly process begins with disassembling a large, slow-speed vertical water pump motor. Technicians perform random winding of a multiple-strand stator coil and layer winding for a rotating field coil. The rotating exciter rotor also undergoes random winding. Various stages of stator lamination replacement are shown on a 3,500 kilowatts generator. Laser-guided tool is used for precise commutator undercutting on a large rotor. The process includes winding and insulating both AC and DC armatures. Coils are inserted and wedged into newly wound stators. Each step highlights high precision and craftsmanship in restoring motors of all types and sizes to optimal working condition. The cylinder head manufacturing process begins with CAD modeling and computer-aided analysis. Patterns and cores are made and placed accurately to form internal passages. Core packs are assembled and molds are constructed, followed by drying and final mold assembly. Molten metal is poured into the mold to cast the part. After cooling, the casting is trimmed to remove excess material. It then undergoes 5-axis machining for precise shaping. Detailing and decking ensure flatness and surface finish. The cylinder head is tested for pressure, leaks, and vacuum integrity. Dimensional tests follow, including chamber volume, valve install and height, valve guide tolerance, and spark plug inspection. Dowel positions are measured relative to the inlet face and engine block. Finally, batch porosity tests ensure casting quality. Ballast is transported and discharged along the track using hopper wagons pulled by locomotives. Tamping machines then compress the ballast under the sleepers with vibration to adjust the track to its final position. Ballast regulators and stabilizers ensure precise alignment and compaction. For rail continuity, long bars and turnout components are welded on site using aluminothermic welding. Thanks to advanced machinery and efficient processes, Amathia successfully achieved 27 kilometers of high-speed track installation per month. The round steel pipes are fed into the forming section, where rollers gradually shape them. Through a series of roll-forming stages, the round pipes are precisely compressed and formed into square pipes with consistent dimensions. In the open die forging process at Schmiedewerke Groditz, high-alloy steel blocks weighing up to 75 tons are forged into custom shapes. Using hydraulic presses, the heated steel is compressed and elongated to achieve the desired geometry. This is followed by thermal treatment in advanced heat treatment facilities to enhance mechanical properties before final machining. The grinding process begins with simple operation and setup. The circular blade is clamped, and the grinding process begins automatically. A laser measuring device tracks the surface and outer contour, correcting even the smallest deviations. The sawtooth grinder, which allows for a variety of tooth shapes, is used. After the initial grinding, the saw teeth are reground to ensure accuracy. Finally, a side cutting process is performed to fine-tune the cutting edge. Throughout the process, a 6-axis CNC system ensures accuracy and repeatability for high-performance slicing applications. The hook is submerged in a pressurized water tank to simulate deep-sea conditions. Technicians monitor for leaks to ensure 100% sealing. Bubbles are checked as indicators of failure. This underwater test validates the product's performance against extreme pressure and corrosion in subsea environments. The 6,300-ton press at Chelyabinsk Forge and Press Plant forms heated steel billets through vertical forging. A manipulator places the billet on the die, and the massive press applies intense pressure to shape the part. The process is precisely controlled, ensuring uniform deformation. After pressing, the forged piece is removed and cooled. This high-capacity line boosts efficiency, reduces workload on older equipment, and ensures consistent, large-scale production of complex metal components. The machining process begins by securing a large metal workpiece onto the dynamic NC swiveling rotary table of the Hermle C60 UMT. Using the TNC 640 control unit, the machine performs 5-axis simultaneous machining with high-speed spindles reaching up to 18,000 revolutions per minute. The table rotates and swivels precisely within 130 degrees, enabling complex contouring without repositioning the part. The AC axis speeds reach up to 400 revolutions per minute, allowing efficient turning operations. High-speed cutting is applied to all surfaces using different tools, which are automatically changed during the process. The rapid traverse of 50 meters per minute enhances cycle time, and real-time feedback from the control unit ensures high accuracy. Thanks to its advanced kinematics and dynamic table, the machine efficiently handles heavy parts up to 2,500 kg with improved cutting performance and productivity gains of up to 17%. The iron block is heated until red hot, then hammered into a cylinder. It is then placed in a closed mold to be hammered into shape. It is punched in the middle and expanded by forging to form a rough ring. The ring is gradually expanded using a ring rolling mill. Finally, after forming a metal ring, the worker uses a tool to remove it from the closed mold. The M3-5AX and M4-5AX 5-axis machining centers perform advanced metal cutting operations with high precision and stability, suitable for complex mold geometries and hard-to-machine materials. Both machines feature a high-rigidity rotary table, with A-axis tilting 120 degrees and C-axis full 360 degrees rotation, driven by roller gears with 0.0001 degrees resolution, ensuring backlash-free and thermally stable performance. During machining, the M3-5AX demonstrates efficient face milling of KP4M mold steel using a 33 mm diameter tool at 6,000 mm per minute feed and 1 mm axial depth, reaching a material removal rate of 144 cc per minute. Another cycle employs a 50 mm cutter at 1,800 mm per minute and 2 mm axial depth for 180 cc per minute removal. For aluminum, high-speed face milling is achieved using the cutter. The M4-5AX, with its high-torque spindle up to 1,009 Nm, excels in difficult material machining. It performs face milling of Inconel 718 with a 63 mm ceramic cutter at 3,600 mm per minute feed and 4 mm depth, achieving a 504 cc per minute removal rate at 95% spindle load. The machine also handles tapping of carbon steel and shell end milling of alloy, supported by a twin drive Y-axis, scale feedback on all axes, and a cooling system that minimizes thermal distortion during continuous heavy-duty cutting. The steel forging process is a sophisticated manufacturing sequence designed to transform raw steel into high-performance forged components with superior mechanical properties. The process involves precise material preparation, controlled heating, deformation, heat treatment, finishing, and rigorous quality assurance, and is specifically designed to produce components for demanding applications in industries such as automotive, aerospace, and heavy machinery. The process begins with the selection and preparation of raw steel, typically in billet or ingot form, sourced from certified chemically composed steel mills. These billets, typically cylindrical or rectangular in shape, are cut to precise lengths using high-powered hydraulic shears or band saws. Cutting systems that ensure dimensional consistency, with tolerances typically within plus or minus 2 mm to meet forging requirements. Steel grades, such as carbon, alloy, or tool steels, are selected based on the mechanical properties required for the final component, such as tensile strength or fatigue resistance. The prepared billets are then heated in industrial furnaces to reach forging temperatures, typically ranging from 1,100 degrees Celsius to 1,300 degrees Celsius, depending on the composition and phase transformation characteristics of the steel. The video shows continuous or batch furnaces, typically gas-fired or electrically fired, equipped with precise temperature control systems to ensure uniform heating. Thermometers or thermocouples monitor the billet temperature, maintaining it within 10 degrees Celsius to optimize ductility and minimize thermal gradients. The heated billets, glowing a uniform red-orange color, are transferred to the forging station using automated controls or overhead cranes to ensure rapid processing and minimize heat loss. Forging, the core deformation process, is performed using a variety of techniques, with the video highlighting open die forging, closed die forging, and hammer forging. In open die forging, the heated billet is placed on a flat or contoured anvil and deformed using a hydraulic press or mechanical hammer that exerts forces of up to 10,000 kilonewtons. The operator or robot operator rotates and positions the billet to achieve incremental shape changes, reducing the cross-sectional area or stretching the material. This method is used for larger, less complex components. Closed die forging, the hallmark, involves placing the heated billet into precision machine die cavities that reflect the final component shape. The dies, typically made from high-strength tool steel such as H13, are mounted on hydraulic presses or back-blow hammers that exert forces of 5,000 to 50,000 kilonewtons. Process for complex parts such as crankshafts, connecting rods, and gear blanks, in which steel is flowed to fill a die cavity under high pressure, achieving tight tolerances of up to plus or minus 0.5 millimeters. The die is lubricated with a graphite or water-based lubricant to reduce friction and prevent sticking, ensuring smooth extrusion of the forged part. Excess material or flash formed during closed die forging is removed during trimming. Hydraulic trimming presses are equipped with flash-cutting dies, leaving clean edges on the forged blank. This step is critical for achieving net shape or near net shape components, where flash typically accounts for 10 to 20% of the billet weight. The trimmed forging blanks are cooled in a controlled environment to avoid distortion, usually on a cooling rack or conveyor. This is followed by heat treatment to enhance the mechanical properties of the forged blank, such as hardness, toughness, and fatigue strength. Processes such as quenching, tempering, and normalizing are carried out in specialized furnaces. For quenching, forgings are reheated to the austenitizing temperature, typically 850 to 900 degrees Celsius for alloy steels, and rapidly cooled in oil, water, or a polymer quench to form a martensitic microstructure. Automatic quenching baths are equipped with agitators to ensure a uniform cooling rate, typically 50 to 100 degrees Celsius per second, to minimize residual stresses. This is followed by a quenching process at 500 to 650 degrees Celsius to reduce brittleness and achieve the desired balance between hardness and ductility. Normalizing, used for some components, involves air cooling to refine the grain structure, after which the parts are removed from the furnace and cooled on racks. Surface treatment is used to remove scale and improve surface quality. This is followed by shot blasting, in which the forgings are shot with steel balls of 0.5 to 2 millimeters diameter at a high speed of 50 to 70 meters per second in an automatic shot blasting cabinet. This process removes oxides, This process removes the oxide layers formed during the heating and forging process, achieving a rough surface. Some components undergo an acid bath to further clean the surface, although this is less common and not clearly shown. Machining is an important finishing step to achieve precise dimensions and surface finishes. CNC machining centers, lathes, and milling machines process forgings with tolerances as low as 0.01 millimeters. For example, crankshafts are machined to form bearing surfaces with tools such as carbide inserts cutting at speeds of 100 to 200 meters per minute. Automatic tool changers and multi-axis machines ensure high throughput, as seen in rotating workpieces and precise tool paths. Coolants, such as water-based emulsions, are used to reduce heat and extend tool life. Emphasis is placed on integrated quality control at multiple stages. Non-destructive testing methods, including ultrasonic testing and magnetic particle testing, detect internal and surface defects. UT uses high-frequency sound waves to identify voids or inclusions, while MPI applies magnetic fields and fluorescent particles to detect surface cracks as small as 0.1 millimeters. Technicians operate UT scanners and MPI tables, ensuring compliance with standards. Dimensional inspection is performed using a coordinate measuring machine with a probe accuracy of 8, verifying geometry against the CAD model. The final stage involves packaging and preparation for shipping. We see forgings coated with anti-corrosion oil to prevent rust during storage and shipping. Components are stacked in steel crates or on pallets, secured with straps, and handled by overhead cranes or forklifts. An automated labeling system ensures traceability, with each package marked with the part number, batch code, and customer specifications. Advanced automation and Industry 4.0 technology are integrated throughout the process. Programmable logic controllers and data acquisition and monitoring systems monitor furnace temperatures, pressure, and processing parameters in real time. The robotic arm handles bills weighing up to 500 kilograms, while sensors monitor the material flow and detect irregularities, ensuring process stability. The combination of skilled labor and automation achieves high productivity, with cycle times as low as 10 to 30 seconds for closed die forging. This technical process, as described, highlights the Czech forging industry's ability to produce steel components with exceptional strength, precision, and reliability. The use of advanced equipment, strict quality control, and optimized working processes ensure that forged products meet the stringent requirements of modern engineering applications, maintaining dimensional accuracy, metallurgical integrity, and performance under severe conditions. Workers dismantle turbine components, install scaffolding, and perform mechanical upgrades as part of the refurbishment of Sobradinho's generating units. Winding, soldering, stacking, welding, assembling, testing. The pre-forging process for the production of S4-5C steel couplings involves a series of carefully controlled steps to transform a raw cylindrical billet into a strong functional component using open die forging techniques. This process, which relies on skilled craftsmanship and heavy machinery, shapes the material without the need for preformed dies, achieving a near net-shape coupling suitable for high-strength applications. The following details the manufacturing steps, focusing solely on the forging process. process begins with a billet of S4-5C carbon steel selected for its favorable mechanical properties, including a tensile strength of approximately 600 to 700 megapascals and good machinability. The cylindrical billet, typically 100 to 150 millimeters in diameter, is heated in a gas or electric furnace to a forging temperature of 1,150 to 1,250 degrees Celsius. The workpiece glows a uniform bright orange-red, indicating that it has reached the austenitic phase for optimum ductility. Temperatures are monitored with a thermometer to maintain a tolerance of plus or minus 10 degrees Celsius, ensuring uniform deformation and minimizing thermal gradients. The heated workpiece is quickly transferred to the forging station using heavy-duty clamps or mechanical controls to avoid heat loss, which can affect formability. The forging operation begins with the reverse, which is performed on a flat anvil under a hydraulic forging hammer that produces a force of 5,000 to 10,000 kilonewtons. The operator uses a hydraulic hammer to strike the workpiece multiple times, compressing it axially to reduce its length and increase its diameter to approximately 300 to 400 millimeters. The operator rotates the workpiece using a clamp, ensuring symmetrical deformation. This step forms the rough, disc-like shape that forms the base for the coupling body, with controlled blows of the hammer maintaining a deformation rate of 10 to 20 millimeters per blow. Operator skill is critical, as free-form forging relies on manual positioning to achieve the desired shape without dead ends. Next, the forging is shaped to develop specific joint features, including a central shaft and outer flange. The operator manipulates the blank under the hammer to stretch and flatten the target areas. The hammer die, typically flat or slightly contoured, is used to form a wide circular base while raising the central protrusion for the shaft. The forging is rotated in steps, with blows applied at precise angles to achieve a stepped profile, maintaining a dimensional tolerance of plus or minus 5 millimeters. The operator adjusts the force and frequency of blows, typically 2 to 3 times per second, to control material flow and ensure uniformity across the surface of the forging, which ranges from 300 to 500 millimeters in diameter. Surface scale, a brittle oxide layer formed during heating, is removed to improve quality. This is followed by a descaling operation, in which the hot forging is brushed with a wire tool or lightly hammered to remove scale, achieving a cleaner surface with a roughness of approximately raw 6.3 micrometers. This step prevents surface defects from affecting subsequent forming or final properties. The forging is further refined to shape the contour of the fitting. The operator hammers the shaft to increase its height by 50 to 100 millimeters, while flattening the flange to a thickness of 30 to 50 millimeters. The operator uses precise movements to ensure the shaft is centered and the flange is even, checking progress visually or with a basic caliper. The final forging step adjusts the overall height, with the hammer compressing the forging longitudinally to achieve the target dimensions, ensuring the shaft and flange meet design specifications. After forging, The coupling is air-cooled on a stand, as shown, to prevent thermal stresses that could cause cracking in the S45C steel. The slow cooling rate, approximately 10 to 20 degrees Celsius per minute, maintains the integrity of the forging. The resulting component, with a rough but functional shape, is ready for machining to exacting tolerances, although this is not shown. This free-form forging process, combining skilled craftsmanship with robust equipment, produces a high-strength and durability S45C coupling, optimized for demanding mechanical applications.